Hello, everyone. So as promised, today we are going to do the logarithmic functions and logarithmic equations with logarithmic equations. Remember last time when we did the exponential equations and we said the exponents and the logarithms are inverse functions? Of course, if the base is the same. So for example, what is the inverse? So let's write first the how we write logarithms, and then we look at some rules of logarithm to compare those to the exponential properties that we talked about. So when I say, for example, log, I would have a number at the bottom we call the base of 8. When I write it like that, I mean, what power should I raise 2 to get 8? I know that 2 raised to the first power is 2. Raised to the second power is 4. Raised to the third power is 8. So the answer is 3. So you can read it as follows. This is read like 2 to the power of 3 equals 8. 2 to the power of 3 equals 8. So that's how we write it logarithmic. And we say that the power and the logarithm are inverse functions. So if I have an equation like that, so let me write it again. So if I say log to the base 2 of 8 equals 3, to get rid of the log to the base 8, I have to take this to the base 2, I'm sorry. I have to take this 2 and raise it to the power of the left-hand side. Why? Because the power 2 to the third or 2 to anything is the reciprocal of log to the base 2. Now, what I'm doing actually is that I'm canceling these together and I get 2 cubed equals 8. It's exactly like the square root and the square, like the positive and negative, like the times and divided by, like, the sign, as you will see later, and the inverse sign, and so on and so forth. There are many, infinite number of functions that have inverses. So when you apply the function to its inverse, it's like they cancel each other. Okay? Like we said, x plus 4 equals something, you subtract 4 to get the x. Log to the base 2, you raise 2 to that power, and vice versa. If it tells me log 2 to the 2 cube is 8, I can take log to the base 2 and apply it to both sides. Because this guy and that guy cancel each other, and I get log to the base 2 of 8 equals 3. So I can raise the base to the power of the log, or I can raise the log to the power of the base. I'm sorry, I take the log of the base, and they cancel each other. So let's first write some examples that would be like the inverse of what we did to the exponentiation. So for example, if I say log to any base. So I'm always going to use b for base. I mean, b, if it's, we'll say that later, but this b is the same as 2 or 4 or 1/2 or any number. If this number is 10, we don't write it. If I say log, it means, and I don't write a base, it means base 10. Okay, so log of 100 is 2. Why? Because 10 square or 10 to the power of 2 is 100. Log 1 million is 6 because 10 to the 6th power is 1 million, and so on and so forth. Also, if that base is e, we don't write log to the base e, we say natural log or ln. So ln meaning natural log or Neperian log. So log to the base b of any number a, okay? But suppose this a, or instead of a, I'm going to say it's a times c. I'm not going to use b because b is for. That becomes log to the base b of a plus log to the base b of c. Huh, that's almost opposite to what we've been doing when we said prior to that is x to the power of a times x to the power, or I should have written b, but it doesn't matter, to the power of c equals x to the power of a plus c. Notice that here I was multiplying x to the something and I added the answer. Here I'm taking the log of two things multiplied. So it's like it's basically the inverse of what I was doing there. Um, so likewise, if I write log to the base b of a over c, that becomes log to the base b of a minus log to the base b of c. Like we said here, x to the a divided by x to the c equals x to the a minus c. I'm just showing you division, subtraction, multiplication, addition. We also wrote log to the base b of a raised to the power of c. That becomes c times log to the base b of a. So the exponent goes down and becomes a multiplier. Here it was x to the a raised to the power of c equals x to the ac. Well, it's not pretty much the same, but the idea was, um, um, I'm trying to show you something similar. And if I say um, log to the base b of the c's power of a, that becomes 1 over c log to the base b of a. Why? Because notice that we were able to write this as log to the base b. If you remember from last time, the cube or the c's root of a can be written a to the power of 1 over c, right? Remember when we said square root of x is x to the 1/2, cube root of x is x to the 1/3, and so on. So c's root of a is a to the power of 1 over c. And then I apply this. 1 over c becomes a multiplier instead of being an exponent. This logarithmic approach, oh, notice something else. Log of 1 to the base b of any base b of 1 equals 0. Here we were saying x to the 0 equals 1. What else did I want to say? Here we were saying the c's root of x to the a is x to the a over c. So 1 over c here is just became a multiplier, like the c here became a multiplier. But these are log to the base b of 1 over x equals negative log to the base b of x. And here we used to say 1 over x to the a equals x to the negative a. So these rules are like similar, quite similar to what we had before, but they would allow us to solve problems um, using logarithm if we have like an exponential function and that exponential function didn't have um, like the same base. Remember? So let's take an example of the previous session where we, for example, let's say if I say 2 to the 3x, whatever, plus 4 equals 10. Remember last time, I think we had like a 3 and 27, and I told you if the 27 was 25, there is no way we can, you know, I think that it was 5. Oh, no, it was 3 and 27. And we said if it was 3 and 25, we cannot use exponentiation rules to solve it. But now, if I have an equation like that and I want to solve it, I would use log. And what log? I can take log to both sides. So I can say, um, for example, log, or I can use even log to the base 2. It's up to you really what to do. You can use base 10 or base 2. So if I say log to the base 2 of 2 to the 3x plus 4 equals log to the base 2 of 10. Now, this is an exponent. It becomes a multiplier. So, and then I get 3x plus 4. And that's what would be left is log to the base 2 of 2, which is 1. They cancel each other. These are 2 to some power, and you take the log to the same base, they cancel each other. And you get the left-hand side is just 3x plus 4 equals log to the base 2 of 10. So 3x equals log to the base 2 of 10 minus 4. Let me put this so you don't think the 4 is subtracted from the 10. And finally, x equals log to the base 2 of 10 minus 4 over 3. And you say, but how do I know that? Now, in this case, you use your calculator. And you'd say, but how can I use a calculator for a log of anything other than, of a base other than 10 or e? You can't. So what do we do? We revert to a new law that says if I take log to the base b of a number, let's say a, I can write this as log to the base 10, which is log without a base of a, divided by log without a base of b. Or it's natural log of a divided by natural log of b. This is a very powerful law that would help us solve this problem. So this problem can be written as log to the base 10 of 10, which is 1, by the way. I wrote the 10, but we don't write it. I'm just writing it for you so you can see. Divided by log to the base 10 of 2, that is the first term, minus 4 over 3. Or I can write it as natural log of 10 over natural log of 2 minus 4 over 3. Here's a calculator. Let's find this value of x. Oh, yeah. Oh, my God. This was from a long time ago. So if I take log of 10, which is 1, by the way, as you can see, right? So 1 divided by log of 2 minus 4. And then I divide the total by 3. I get x equals negative 0.226. Let's replace it by natural log. So I say natural log of 10. Oops, let me open parentheses here first. Divided by natural log of 2 minus 4, close the parentheses and divide by 3. I get the same exact answer. Now if I take 2 raised to the power of 3 times that plus 4, what do you expect to get? I should get a number very close to 10, like probably because of approximation, I think. I don't know, I didn't do it. Yeah, 9.9999, which is 10. So that's how you check your answer to see that we didn't have any error. And that's a very powerful law that you really need. Okay, so that was to solve exponential equations when you don't have the same base or the bases are not related power-wise to each other. But now let's take some examples on logarithmic equations. Okay, so let's say, let's take this calculator. Let's say I have example log to any base, like to base 9, for example, of like, let's pick some numbers, square root of x. Let's make it even, or maybe you can make it a cube root, okay? Log to the base 9 of 5x minus 2 equals 0. Now, how do I get rid of log? First of all, I have log minus log. Remember how we simplified that? It's the opposite of what we showed you here. Log to the base b minus log to the same base, you can write it as log 1 over the other, the first over the second. So I can write this as log to the base 9 of root x divided by 5x minus 2 equals 0. Okay, so I simplify that as a single log. Why do I want to do that? Because now, no, I can raise 9 to this power equals 9 to this power. Without it, I cannot do. It's not correct to say, oh, let me take 9 to this power minus 9 to this power equal. No, that doesn't work. It's only applied when you have a single log on one side, not two. So you have to combine them first. Be careful. This is not correct to say 9 to this power minus 9 to this power equals that, and then you divide. That would be incorrect. Okay? So I will take 9 to this power and 9 to this power. The 9 and the log to the base 9 cancel each other. So the left-hand side becomes root x over 5x minus 2 equals anything to the power of 0 is 1. So this equals that. That means when you multiply both sides by 5x minus 2, you get root x equals 5x minus 2. Remember that? That's exactly what happened when we square the square root by introducing an erroneous answer. I don't know if that would give us, let's see if I square both sides, because now it became a root, so to speak, equation, like a radical equation. The left-hand side becomes x. The right-hand side is 25x squared minus 20x plus 4. I'm going to subtract x from both sides. And I will get 25x squared minus 21x plus 4 equals 0. I can use the calculator to find x, which in this case would be 21 negative b plus or minus the square root of 441 minus 400 over 50 equals 21 plus or minus root 41 over 50. So I get x, the first one is 0.548. And the second one, you just change that into minus, and you get 0.292 if you use 3 decimal places. Now you have to go back and check to see that. The check will not be easy because that's a log to the base 9, and we don't have log to the base 9 in our calculator. So you have to do, unfortunately, you have to do, say, log of square root of x divided by log of 9 minus log of 5x minus 2 over log of 9 and see if they are the same. So I can take log of the square root of the first value, which is 5, 4, whatever, divided by log of 9 equals. So the left hand, or the first one is that. Let's take the next one, minus log. So I'm going to take log of 5 times the 0.48 whatever minus 2 divided by log of 9. And I got the same exact value. So when I subtract them, I will get 0. So the first one is correct. Let's check the other one. So I'm going to say log square root of this guy, which is 0.2919 over log 9, and I got negative 0.28. Let's go to the left-hand side, or the second term, I meant. Log of 5 times 0.29, this guy, minus 2, divided by log 9. In fact, I didn't have to divide both by log 9 if the numerators are the same. And I got the same answer, so both work. But that I was giving you a very complicated problem. The base is hard so that we learn that we can use natural log or log. And to make the transformation so we can check our answer. Let's pick another example. Let's say log x, so to the base 10, that's a plus log, say x minus 1 equals log 3x plus 12. So what do I do when I have 3 of those? You have to combine 2 together. So I have to combine these 2 or move this to the other side and combine 2. It doesn't matter, but you cannot deal with them as separate values. Again, exactly like the log to the base 9 before. I cannot say 10 to this plus 10 to that equal 10 to, no. 10 to 1 log equals 10 to the power of 1 log. You cannot do it addition because the addition here is not correct. Remember, we have multiplication becomes correct. So when I have 2 logs like that, I simplify them as log of x times x minus 1 equals log of 3x plus 12. If the log of the first equal log of the second, so the first equal the second. But to show work, we say, oh, if I raise 10 to both sides, it's better to write it this way, just to show that you're applying an inverse function. But it makes sense. If I say square root of x equals square root of y, then x equals y. I don't have to square both sides, but it's better. So x times x minus 1 is x squared minus x equals 3x plus 12. I'm going to subtract, move everything to the left, so subtract 3x minus 12. So I get x squared minus 4x minus 12 equals 0. I have to be careful here because I will have two answers I have to check. So, and you will see why. X minus 6 times x plus 2 equals 0. So either x equals 6 or x equals negative 2. Right there, you should be worried because if x is negative and you take log of negative 2, it's infinity. So I know that this one doesn't work. You cannot have a negative. This one also would be log of negative 3, right? This one is okay, but these are not. Why is this important? Because if x is negative 2, you are saying log of negative 2 plus log of negative 3, and you say, oh, this is, I know that if I have two logs, I multiply them, I multiply what's inside. So it's the same of log negative 2 times negative 3, which is positive 6. No, that is not correct. Because log of negative 2 is undefined, log of negative 3 is undefined. It's like a very common thing. If I say, what is the square root of negative 2 times the square root of negative 2? The answer is negative 2. It's not 2. Right? Well, when we do the imaginary, I will go more deeper into that. But let's check the 6. It's telling me log of 6 plus log of 5, 6 minus 1, equals log of 3 times 6 plus 12. Notice that log of 6 plus log of 5 is log of 6 times 5, or log of 30. And 18 plus 20 is 30. So this is okay. It's a unique answer, very similar to the radical equations. You have to check with the log. And I said that, I believe, when we did that session. I told you to be careful to check your answers, especially that here the negative sign will show up a lot of time. We'll take two more examples. Let's see if I have something in. Yeah, let's take something that log to the base 5, and this one says 2x plus 4 equals 2. This is exactly what we did earlier. Pretty much the first thing. I told you when you have a log to some base of something equals a number, we take 2 to the power of 3 equal that. So 5 to the power of 2 equals that. But it's again the same thing as saying, let's take 5 to the power of the left-hand side equals 5 to the power of the right-hand side. The reason we write it like that is that we show that we understand the meaning of logarithm, is that these two are inverse functions. Now these cancel each other, so the left-hand side becomes 2x plus 4. 5 squared is 25. I subtract 4 from both sides, so I get 2x equals 21, or x equals 21 halves, or 10.5. Okay. Finally, let's take one last example so we cover all the bases, so to speak, of this topic. log to the base 2. I should use something with different bases. X squared minus 6x equals 3 plus log to the base 2 of 1 minus x. I just didn't want to make on the fly some examples from my head and the numbers won't work. So what do you do when you have something like that? How would you solve? Definitely, if you have logs and constants, you move the logs to the same side first. So I have to subtract log to the base 2 of 1 minus x from both sides, because otherwise you cannot proceed. That becomes 0, and the left-hand side now can be combined because I have a log to the base 2 minus a log to the base 2 equals log to the base 2 of x squared minus 6x over 1 minus x. And that equals 3. And now I'm going to take 2 raised to this power equals 2 raised to this power like we did before. So we cancel that. So you get x squared minus 6x over 1 minus x equals 8. You multiply both sides by 1 minus x. So you get x squared minus 6x equals 8 minus 8x. Then you add 8x minus 8 to both sides, and you get a quadratic equation, x squared plus 2x minus 8 equals 0. Minus 8 meaning x plus 4 times x minus 2. The numbers multiply to negative 8 and add to positive. So you get x equals negative 4 or x equals 2. Some people will say, oh, that cannot be true because it's negative. No, that isn't correct. You have to check and see if the quantity between parentheses is negative, not if x is negative. So let's try x equals negative 4. That becomes log, the left-hand side becomes log to the base 2 of x squared, which is negative 4 squared or 16, minus 6 times negative 4 is plus 24. So the left-hand side is log to the base 2 of 40. The right-hand side is 3 plus log to the base 2 of 1 minus negative 4, which is 1 plus 4 or 5. Notice that that becomes log to the base 2 of 40. You can use a calculator to do that. 3 is log to the base 2 of 3, right? Of 8, right? And I can combine the addition by multiplying these two guys. So it's log to the base 2 of 8 times 5, which is log to the base 2 of 40. So yes, x equals negative 4 is correct. So because x is negative doesn't mean it's not a correct answer. You have to check. Of course, you can use your calculator. I'm doing it manually, but you can use your calculator and check right away. Now, how about x equals 2? Right there, you have to say it's cannot work. Why? Because the left-hand side, you would say log to the base 2 of x squared. If x is 2, then x squared is 4 minus 6 times 2 minus 12. 4 minus 12 is negative 8, and there is no logarithm of negative numbers. So this one is not correct. So this example was just to show you that you can have a negative answer for x as long as the log itself is positive. So I'm going to stop here. I think we covered all the bases here for logarithmic equations. And as usual, if you have any question, please let me know in the comment session, and I will come back to you as soon as I can. Thanks for your time. Hope to see you later. Bye.